would like for y'all to write down the process of pH dependent charge. Test your ability. What are the three sources of pH dependent charge?
Three sources.
Well, no, we're gonna do the whole.
Okay.
Yeah, like I'm wanting you to describe the process. So what are the three sources of pH dependent charge?
Broken edges of clay.
Broken edges of clay.
Iron and aluminum oxide.
Aluminum iron oxide. Good job, Nathan. What's the last one?
Functional groups of organic.
Functional groups of organic matter. So that's the one that we're primarily concerned with, right? It says functional groups. And so what happens when we add lime? Which ion are we adding to the soil? Hydroxyls. soil is always trying to do what?
Maintain a balance.
Maintain a balance. Thank you, Dr. Fenwell. Which we call that balance what? Equilibrium. So in order to meet that equilibrium, what happens? Did y'all get enough where you were written, where you were like, all right, I'm spent? Or did you have more? Okay. That was more so just to kind of get you to go, uh-oh. Might need to think about this a little bit more. We add lime to our soil in the spring. Increase the hydroxyl concentration. In order to form the equilibrium, the hydrogens dissociate from the functional groups of organic matter to form water. Leaving this negative charge on this functional group of organic matter. And this is going to be important like near the end of this class, and I bring it back to pH-dependent charge. So this negative that was associated with that hydrogen that dissociated is how we increase our CEC when we increase our pH. Because the soil is trying to meet an equilibrium, it's trying to get back to more acidic. And y'all, again, we're talking that those changes are between 6 and 7. Not that it's trying to get all the way back to 5. But there is that balance back and forth that when we raise our pH to 7.4, it's still trying to get back to 7. And then when we have a soil that's 6.3, it's trying to get back to 7. Just there's too many hydrogens or too many hydroxyls that are stopping that. So now we have this water formation, these little water molecules. We have added fertilizer and made our soils acidic through the process of nitrification. So now we have added back hydrogens to the soil, and now our pH has become 5.7. It's just that it's not neutral anymore, or it's not alcohol. It's becoming more acidic. My feet are going to stick to the floor all day. Because we're trying to reach that equilibrium of 7, these hydrogens will now associate with the functional groups of organic matter, creating back to where we started, right? So now this organic matter is in equilibrium. In certain cases where we have a very acidic soil, the hydrogen can protonate the hydroxyl and cause a positive charge. Making better sense now? Okay. There's probably going to be like a discussion question. Explain the process of pH-dependent charge.
Can you go back one slide?
Sure. This one?
Yeah. That's good.
Can you go all the way
Just
back?
figure out which one was supposed to be. Yeah. That is.
All right. And so you can watch the video and follow right along like it was the words. It's the dissociation, it's the association, more alkaline, more acidic. Those are the terms that I'm going to be looking for. Those are the terms that will make you correct when you go to speak to whoever it is that you're speaking to. My boss used to call it bar stool because I would just say, well, it just became more negative. Or I would just say some stuff like, the nitrogen disappeared. So hydrogens dissociate, form water, leave that negative charge. We add fertilizer, our soils become more acidic. Those hydrogens will again now associate or protonate, really. They'll protonate that oxygen, forming this hydroxyl, which is now at equilibrium. If we continue to have a greater acidity, the soils will supply hydrogens, and those hydrogens can protonate the hydroxyl, causing a positive charge. And so now we would hold on to anions. So if the pH is low, which ions are we going to be able to retain more of? Which ion, like our nutrients? We only have two types. There's either cations or anions. Anions. So in acidic, anions. Acidic, anions. So in acidic soils, we will be able to retain more anions. In alkaline soils, we will be able to retain more cations. So acidic, anions, and then you can think alkaline, cations, there's the K in there, and also that in order to get our soils to become alkaline, we apply lime, which is what's the component of lime?
Calcium carbonate.
Calcium carbonate. So when we add the calcium, we're going to increase the alkalinity, and therefore we'll increase the CEC, which is the cation exchange capacity. So how do you manipulate the CEC of the soil? Add lime. pH dependent charge is going to allow you to be able to retain more cations. We talked about the reversibility.
You said this is all gonna be online and.
Yeah, sure. I've got all this stuff. I posted the lecture
Okay.
from yesterday or Tuesday, and so what that is you'll have to go into iLearn, click under content or course material content, and then lectures, and there should be a YouTube link. I think YouTube is a much better way of getting you to those videos. For some reason, I just think that it would work like regular internet rather than having to go into the cloud. Like it's stored on that YouTube channel somewhere. They're dealing with it. And then all the lectures will be in order. Okay? Yeah, no, I wasn't going to just leave you out there to dry. Like I know it's a lot to ingest.
I think I last checked Monday or Tuesday morning, so I haven't checked since you put it on there.
Yeah, no, I put them up there. I mean, Tuesday
Okay.
night. We really only had 2 lectures. Remember, and then that one I was in super slow-mo. Also, this reversibility and charge equivalence is going to be a big deal. When we think about reversibility, we're thinking about the 2 arrows that go back and forth. So I think this is about where we made it to last time. Last time it might have been written as the ionic double layer. I changed that. It is now the diffuse double layer. So when you look in your notes again, you'll see me refer to it as the DDL, the diffuse double layer. We talked about those cations, and we have 2 types of complexes, outer sphere and inner sphere. Here we have this calcium, and we have a water molecule attached to the calcium. That water molecule forms a bond with the oxygen in the tetrahedral layer. This is a hydrogen bond. This is a covalent bond. And these are going to be important for our adsorption, also especially for our anion exchange capacity, pesticides, and our groundwater contamination. These are the ways that we can purify our water sources by changing the ion or complexing them with something that complexes with the soil. I mean, it's simple magnetism, really. And then the partitioning coefficients are going to kind of go into, you can look on the label and know at what pH your soil will desorb or adsorb these pesticides. And the way that looks like in real life is a producer applies a pesticide and then wants to know why it didn't work, and the pH was off, and therefore the herbicide was desorbed to the soil and not, or adsorbed to the soil and not absorbed into the plant based on the pH, because the pH influences this complexation and then holds that herbicide, that organic chemical, to the soil and will not let it go. So you applied it, but it didn't work because it didn't get into the plant. It was held too tightly to the soil. So modes of absorption, electrostatic attraction and the formation of the bonds. This is typically what we consider cation exchange capacity. Next, we have this multinuclear surface precipitation. We have hydrophobic partitioning, and then physical entrapment of the soils. And so this multinuclear surface precipitation is when there is a bond formed on the surface of the soil, but not to the soil. There are some other bonds that are going on in there. They all share the same nucleus, and if you can break that nucleus, then that anion, cation, organic, inorganic chemical will then be released into the soil. Way beyond the scope of anything we're going to do in this class. But the physical entrapment of a chemical in pores looks something like this. So if y'all remember back from soils, and maybe Rick or Dr. Branson went over this, I know I did. Remember we talked about that when we have these, some of these silicate structures, they will form voids. And in those voids, potassium can fit in that void, and when this layer shrinks, it will fix that potassium inside this layer and it cannot come back out. And you might get some water that comes in there again, but remember these are non-swelling, so they won't swell too much, but they will hold on to that potassium or that ammonium as part of isomorphic substitution. Not so much that it's going to substitute, but that they're the same size and they can fit in that void. And when they fit in the void and they fill that up, they're locked in there. The charge now becomes balanced and they're not letting go of that. Y'all remember that from soils? So for outer sphere absorption, we have at least one water molecule forming this bond. For inner sphere, we have a direct covalent bond between the chemical and the surface. And then next we can, because it's not just that simple, we have to have more people who want to make it difficult and they want to classify this and whether they have monodentate, bidentate, multinuclear dentate. And what that means is that we're going to have some bond now between aluminum and the oxygen in that. A little bit too much. But just know that there are different types of inner sphere adsorption, and if you kind of have an idea of what that absorption type is, you'll have an idea of what the energy is needed to release that or force that reaction to go to equilibrium and go towards wanting to make this bond or break this bond. Does that make sense? So soil chemistry, knowing all these things, we can start to begin to calculate how to counterbalance them so that we can make it do what we want it to. Outer sphere absorption on the surface of the clay mineral. Electrostatic, and I watched the video, it's kind of like when you rub a balloon on your head, you can stick it to the wall, but at some point the electrostatic stops and that balloon will fall, right? So it's not consistent. It's not like I can just take that, stick it to the wall, and it will stay there forever. Like there is some friction, some electrostatic needs to keep that there. And that's where we get that's how we hold on to our macronutrients, our C. Hopkins Cafe, managed by mine cousin Mopelnini. Most of those would be, some of those are micronutrients, and we use a chelating form, some sort of chelation to hold those to those soil surfaces. And then just some basic stuff, cations are absorbed to negative charges. And how do we get more negative charges? Add lime. Add lime. How do we get more positive charges? Add aluminum or sulfur, something that's going to make the soil acidic. So some of the things that are going to affect is the type of surface charge. And so is that a Ca2 plus? Is that a sodium 1 plus? Is that K1 plus? The valence, ion hydration and types of ion, and concentration. And so these are not something that we like. The way we can manipulate these is through change of oxidation or change of chemical form by bonding it with, like, potassium with chlorine. The ion hydration, there's a table for that somewhere if you ever needed to look that up. The types of ion in solution, and that's going to go to, do you have a lot of calcium? Do you have a lot of bases? Do you have some acidic some acidic or anions, aluminum, iron, hydrogen? The concentration of those ions, do you have a lot of calcium? Because if you have a lot of calcium, then you'll probably have a lot of outer sphere complexes. Not a lot of calcium, then you would have a negative soil, and you might have some inner sphere complexes. Important to know that the reaction is reversible. We can have some of this on the oxides and the organic matter. They will be hydrated on the surface of those functional groups. So that's why the functional groups of organic matter and how they have that charge, the negative charge will allow some of our cations to be adsorbed, but the charge is not strong enough to dehydrate the water from either an anion or a cation. So they will be exchanged or desorbed more readily than inner sphere complex, because there's that little film of water, and that little film of water can, from adhesion and cohesion, can add another water molecule, another one, and eventually it gets far away enough that that balloon does not stick to the wall. Here's where when I took chemistry, and he mentioned this right here, that they cannot. He told me that they didn't know how this worked. They couldn't quantify this. It's still not resolved. They don't have a solid solution for it. They just know that the difference in between how much the outer sphere is and the liquid portion, that is going to be dependent on how much water is in the soil. And that's always changing. Remember, our soils are dynamic, and they're always changing, trying to find some equilibrium, and they never really reach it, do they? So again, here we have hydrogens dissociating from functional groups of organic matter. This negative charge is what bonds our cations. But this negative charge is also not enough to, when we say dehydrate, remember we had the water. I guess I'll do this for Michaela. Remember right here we have this water molecule. So this charge on that, the charge on the organic matter on the negative oxygen on the functional groups of organic matter is kind of the same thing right here, right? We have this oxygen with a negative charge. It's not enough to just pull this hydrogen off. It can only bond because of the charge. Like when we say dehydration, we mean pull that hydrogen off, and now we're left with this OH. Okay? So the charge on this, on the functional groups of organic matter in this is actually an aluminum and iron oxide, is not strong enough to pull just one hydrogen off. So that's how that attraction is. And then this goes along with the reversibility, that when we have a charge equivalence, the reaction can be reversible. So how much, which cations or anions are in solution, and then also what the charge of those cations and anions is going to determine how much these nutrients are adsorbed and desorbed to the diffuse double layer.
So if you added lime to the other one where it wasn't strong enough to dissociate that, would that change that?
This one?
No, the other one. We were talking about the outer sphere and inner sphere, where it wasn't strongly, the picture of it. That.
This one?
Yeah, so where the hydrogen isn't strong enough, or the charge on the oxygen isn't strong enough to dissociate the hydrogen, if you added lime to that, would that change that?
So that lime would pull one of these hydrogens off, and one of those hydrogens off, and one of these off, and one of those, and one of those.
But it still would change the other one.
But it wouldn't change this one.
Okay.
So it's really a one-to-one.
Okay.
That cation exchange right here for this outer sphere complex is one-to-one. It is not these two to that one. It's just a straight 1-to-1. And so you can add more lime, but eventually another hydrogen would attach here, because this one's already attached. Like you wouldn't have it attached, this water molecule, that water molecule, and then this hydrogen with that negative. Right here. How's a better way? Right here. How about this? You see how this hydrogen is one there, and then one there? You wouldn't have these two right here. It can only take one hydrogen off of one water molecule, not both of them. So you could have this one possibly there, just based on how that molecule forms around there. But adding lime would only just change the negative on each one of these. It wouldn't make this one twice as negative. It would need to be 2 times as negative to pull that off. Does that make sense?
Yeah.
Okay. But good thought process on the fact that we can now add lime to our soils and manipulate them in some way, shape, or form. Now, inner sphere complexes are more important, and you'll find these mostly with your kind of transition metals. We have some lanthanides and some actinides, our phosphates and selenate any of the eights and ites, really. It's kind of how I think about it. We have that covalent bonding between the chemical and the mineral of the soil organic matter. You might see it written as chemisorption or specific adsorption, because that is very specific. It's directly bonded to that mineral surface. Our oxyanions, and then along the aluminosilicate edges, oxides, aluminum and iron oxides, and functional groups of organic matter. That's where we're going to get those charges from. Again, it's dependent upon the ion solubility and the ionization energy, and that's what soil chemists sit around and do. They do all the calculations before they go into doing the experiment, and they know exactly how much they do and don't need to add to this solution to make this reaction happen. I'm excited that we got that you can add lime to the soil and change the CEC of it. Same principle though, they're just doing it with different systems. We're just typically doing it in a farming system, and we're only really concerned about, basically, remember I mentioned increasing the cup size. That's it. Now we spent a lot of time in soil chemistry going over this stuff, and y'all don't have any need for it. There's just no purpose of knowing the Debye-Huckel equation, because you're never going to use it. And if you do need to use it, you can always just YouTube it or pay someone to do it, right? And the ability to form those covalent bonds, and then also that is going to be dependent upon the charge in the surface area. So we add lime, we increase the charge on the functional groups of organic matter, we would have more inner sphere adsorption. If we change the charge on the surface property, we would have less. Again, pH dependent charge, functional groups of organic matter, aluminum and iron oxides, broken edges of clays. Everyone was good up to that point. So we've talked about just kind of our cations, which are really more inorganic chemicals, but they have a charge. For our non-ionic chemicals, those that don't have a charge, like organic, which would be pesticides, or it could be herbicides. If we're talking, pesticides, herbicides, and then for our inorganic, we would have like fertilizers, something synthetic, something that we've made. So there can be some hydrogen bonding and van der Waals forces, and we know those are the two strongest forces in chemistry. So when you have organic substances, you can know that you're automatically going to be dealing with a different set of principles surrounding the adsorption and desorption of those chemicals. And inorganic is mostly just for protonation and hydrolysis. If Michaela were here, I'd have her draw urea hydrolysis, but knowing that during that process that we're kicking off a hydrogen. Or actually, hydrolysis would be, if it were aluminum hydrolysis, we would be dissociating a hydrogen. And then they're going to form those covalent bonds with that function. And so desorption is going to be the opposite of adsorption, right? Adsorb, desorb. Most of the times what you will hear people say, scientists, or they'll just call it sorption. No AD or DE, it's just SORPTI, sorption. And we don't know if it's adsorbing or desorbing, and those things are happening, for the most part, very rapidly. And so this is how we release the solid phase. We release solid phase chemicals into the soil solution. And so that all that is just that we have that outer sphere complex where we have this small charge and this bond, and it will just exchange off. And then another one will exchange right back on. And then one will exchange off, and another one will exchange right back on. So those processes, outer sphere desorption, being very rapid. That's going to happen quickly. Now, inner sphere complexes, not so much. And this causes us a problem because now we have to add some energy to the system in order to make this reaction happen. And we can have some reversing, but it's not going to happen at the same rate as we did with the cation exchange reversing. We have a slow diffusion process because y'all remember diffusion is moving from an area of high concentration to low concentration, right? Well, if they never move off the soil colloids, there's no diffusion because there's no area of low concentration, it's all consistent. And so we have to have some activation energy, we have to apply some form of energy, whether it be heat, or chemical, water, something to force a reaction, to force those inner sphere complex anions off of that exchange site. And that exchange is going to be different with adsorption mechanisms. And then we also have to worry about this interlayer collapse, which is where this comes from. So you can have this adsorption, and now it may be that the desorption could happen very easily, but that layer is collapsed and has trapped the potassium or the ammonium inside this clay layer. We'll also have some surface precipitation, and that's just kind of what surface precipitation, it will isolate some of those metal ions, aluminum and iron, tin. It will just isolate those out of the soil solution, almost as like it will reach out and grab it. And this is kind of in the form of chelation. And so chelating just means that it's a claw that it holds on to that and holds on to that metal anion or metal ion and does not allow it to move anymore. Hydrophobic myoceles and supramolecules, way beyond the scope of what we're doing here, but they also isolate some of those chemicals from the bulk soil solution. Is that all I had? I think that's all I made it to.
John, so what's the issue with the strong bonds in the inner sphere? Why? I know you said that it makes it harder for you to. Why do you necessarily need that?
Why am I going? Come on. Right here, they're covalent,
Okay.
so they're sharing electrons in that outer sphere.
So, but why do you necessarily need to make a? What can you say something about the bonds needing to getting more energy to make up?
Sure, because they're sharing. So right here we have this little water molecule, and that's the same thing as.
And you said it could go back and forth and be changing all the time, right?
Correct.
So, but what's the issue with having the other one stay there? I guess is what I'm.
This one won't come off,
Okay.
so now you can't get phosphate,
Okay.
right?
Yeah.
And so if it's held there very tightly, and we have this problem that phosphate's just held to the soil tightly because of these covalent bonds. It forms this inner sphere complex. It's really difficult to get it back. Once it's formed, it's hard to get it back. You can, it's just that there has to be some energy greater than these two, the covalent bond formed here and the covalent bond formed there. So now you have to break two sets of covalent bonds in order to get this out. Once you do that, guess what it's going to do? Whoop. Unless the plant can have some sort of energy enough to pull that off, and there's enough water and the energy of the plant to force that diffusion gradient into the plant. Phosphorus is the primary one that we have this problem with. Sulfate's not so much, and this goes back to here. That because we have this 2 negative right here, So each one of those two negative charges is going to have formed some covalent bond with the clay mineral. Sulfate, maybe not so much. And then nitrate and chlorine would probably be more likely as a outer sphere bond, because we can get nitrate very easily. Chlorine and sulfate, we put a lot of sulfur out. Sometimes it'll stay in the solution. But man, when you put phosphorus out, that's why we put it in a band right next to the plant, because if we were to broadcast it and the plant is over there and the diffusion rate of phosphorus is like this, how long do you think it would take for the plant to get this phosphorus, right? Because it's only first, it's got to overcome the bonds of the phosphorus right there first, that inner sphere complex. It has to overcome those and then use up the phosphorus that it can. And then slowly but surely the rest of the phosphorus will make its way down the diffusion gradient to the concentration, to lower concentration. But I mean, it moves so slow because it has to from here to here, break off from here to there, break off from here to there, break off from here to there. So it just kind of stops at every stop along the way before it finally gets to the plant because of the covalent bonds. Here, this is not covalent. This is me rubbing my balloon, putting it up against the wall. It'll stay there for a moment, but eventually the charge, the electrostatic charge will dissipate. There's no electrostatic charge here. Now we're sharing a covalent bond in our outer shells. No one wants to give that up because now they've reached some equilibrium, right? Covalent bonds where our outer orbital is now satisfied. We don't want to stop being satisfied, so it's just really hard to pull that apart. You can, and that's where it goes into that activation energy where we didn't really go over. Here. That's where this equation applies. And there's some other stuff, like there was another set of equations where it's really just you plug one number in, you do some calculations, and you can figure out which way the equilibrium will shift. And if you can figure out to shift it really hard, really fast this way, that energy that goes in will break that covalent bond, and now you have the opportunity for the plant to take that up. But only if it's really close. You got to be at the right place at the right time and kind of go now, right?
Okay.
So using this equation and some of the things that go along with it, they can determine what they need to do in order to break that covalent bond. Y'all won't do that. It's important to know that phosphorus is held really tightly to the soil. Why? Because it's an inner sphere complex and covalent bond. When we get into our remediation and our pesticides, we'll be able to understand either A, how we can adjust our pH or some other chemical property of the soil to either desorb or adsorb. And that goes into remediation. So I was using, for my selenium, I was changing the oxidation of the environment, which is going to change the valence state from from +6, I was going to change the valence state from +6 to +4. +4 is more held tightly to the soil. So if I can get it to, in the solution, if I can change the oxidation state or change the chemical speciation from one to another with a lower oxidation state that's held more tightly to the soil, that is one way that we can manipulate our soil chemistry, just like our pH, to pull these pollutants out of some water or soil. Likewise, the other way, where they had this problem with selenate, this is held tightly to the soil, so the plants can't necessarily take it up as easy. So this was in a aquatic environment, in a pasture land that's contaminated with soil. We have to manipulate something in order to release those intersphere complexes. All the hard stuff to get out of the soil, intersphere complexes. Great questions. I think that was it. I think that's where we made it. Do we have any questions about anything that we went over? You know how to do pH dependent charge now? What are the 3 sources of pH dependent charge?
Functional groups of organic matter.
Functional
aluminum
groups
iron
of
oxide,
organic matter, aluminum and iron
broken edges of
oxide,
clay.
and broken edges of clay. Awesome job, Nathan. That's it. That stuff should roll off your tongue like instantly, man, because those are going to be the things where you go, how come this isn't working? Well, let's look at the soil. What's the pH? What type of soil is it? Do we have a lot of clays? Broken edges of clays. Aluminum and iron oxides. We applied this chemical and it's not working the way that we thought it was. Why? Well, have you checked the pH? No. That should probably be the first thing you go check is the pH, because that's going to influence everything else that you do with that. And so how do we increase our CEC? Apply lime. How do we decrease it?
Did you say aluminum or sulfate?
Aluminum or sulfur is going to decrease your pH. And we're also doing that naturally over the course of the growing season, because we're applying fertilizer. Remember we talked about we're applying a little bit in the beginning and then a lot at the end. It has to undergo that. It has to undergo a change from ammonium to nitrate, which then leaves hydrogens in the soil. That's why we put lime on after we harvest, so we can give it the time to do the reaction over the season. And then we might apply lime again before we plant, so that by the time the reaction happens, it will offset that. That's all we're going to be doing in ag, is trying to keep an equilibrium and a balance between pH, cation exchange capacity, so that our plants can take the nutrients up.
Did you say you want your pH a little bit higher before you plant, or do you want it equilibrium? Is that what you're saying?
So I mean, typically if you can plant corn somewhere between 6 and 7, you'll be okay. Like it's
I
not.
didn't know if you were saying like add more lime right before you plant, just because I guess when you plant, it's going to take up a lot of nutrients and everything.
Eventually the timeline will change. And you can really just think about this as a calendar. It's gonna be September. This is gonna be March. Right, so we're gonna apply, we're gonna plant in March of 2021. We're gonna apply fertilizer here in April, May. We're gonna apply a little bit of fertilizer right here. That's gonna help our plants grow. And then we're gonna apply a lot of fertilizer. We're gonna apply our first shot. Second shot. Remember we said this was like 150 pounds today. This was like 50. 50 pounds of nitrogen to the acre isn't a lot. Okay, so the change in that, the plants are going to take up most of that. So you're not going to have a big problem with, you're not going to have a big problem with your pH right here, with your ammonium going to nitrate and changing your pH so that your nutrients aren't available. Here you're going to have one. And so by the time that you get to harvest, we have a large release of hydrogen plus ions, right? So when the acidity decreases, the CEC decreases. So taking a soil sample right here isn't really going to do you very much good. But you know you're going to have to apply lime at some point because you know that you did change the pH and it is now acidic. So what you'll do is you'll just say, you know what, we know we're just going to go ahead and apply two tons to the acre right now and allow that. So again, here we have a 2 ton lime application, and we will allow that to do its thing that is calcium hydrolysis, and that will neutralize this acidity. Okay? But it might not neutralize all of it because we don't know how much we did. We can calculate that. We could. No one ever does, but we could. And so then you take a soil sample here in February. And then it will tell you another 1 ton per acre. And so you put this 1 ton per acre out, and it starts to undergo this process. We have a 1 ton application. That is going to help by the time you start to have this large. And plus also, what else are we trying to do right here? What else are we trying to do with this fertilizer application? I mean, lime application.
What are we trying to do with it?
What is going to happen when we apply this fertilizer?
I hope it goes into the soil and diffuses into the plant.
I'm sorry, the lime. When we apply lime, what happens?
Alkalinity goes up.
And when the alkalinity increases, what else increases? The pH. Then what else? The CEC increases, and so when we go to apply our first shot of fertilizer, we can hold everything. When we go to apply this 150 pounds per acre, there's enough CEC to retain the fertilizer that we just applied. So this is kind of like this is kind of putting a whole bunch of coffee or a whole bunch of soda into a cup that can't fill it. You can put 150 pounds there all you want to, but you can only drink what's in the cup. So if you increase the cup by increasing the CEC by adding lime, our pH dependent charge increases, you get a little extra. And so that's one of the reasons right there. Also, when we apply the lime here, we're going to retain some of those nutrients over the winter because our CEC is going to change now also. So some of this ammonium or any of the other nutrients that might not have gotten taken up will then be held. Of course, we're going to plant cover crops, so they need to have a good pH, and they're going to hold some nutrients. And when we apply our lime, this is going to decompose. The microbes need a good environment to be able to thrive in, to break down the cover crops that took up the nutrients that was applied. So it's this big cycle of everything that goes along with it. And each one of these little things that we do has an equal and opposite reaction. Making sense?
Yeah, I like it.
Okay, cool, man. I hope it's making sense, and I hope people are liking it and kind of seeing how it applies. I was thinking this morning, like, I'm not teaching y'all anything new. Not that I didn't already teach you in soils. We're just going over it again and kind of understanding how it applies to what we're about to be doing. And so as it was just introduction, hey, this is a thing. You got your grade and rolled on, thought you were never going to see it again. But so here we are, and that's why it's 3,000, and now we're in 4,000 level classes, and you're starting to see where that applies. You've made it up to the senior level. At 3,000, this would have blown your minds. You agree? If I would have walked into this in a 3,000 level class and started talking about this after pH dependent charges went off on a tangent, I would have been like, whoa, hold up, bro. I'm not even growing for it. Okay? I'm ag engineering. All right? Can we answer everyone's questions? Cool. All right, we'll see y'all in an hour and some change.